Okay, welcome back as we continue with the interpretation of the molecule C9H10N2. So we are now dealing with the carbon NMR. So as you can see, okay, this is the question. Number 3 from the top is the carbon NMR. I'm just going to try to bring it close. So as you can see, we do have about 6 peaks there. The first peak closer to 40 is a quartet. Then we have a peak closer to 100, which is a singlet, a peak at about 110, which is a doublet, and a peak at 120, which is a singlet, and a peak at about 134, I would say, it's a singlet. So this is the magnified appearance. I try to magnify so that you see what's going on. So this is the information that we have regarding the peaks. So it's something interesting because, as you can see, we have 9 carbons in our molecule, but we are seeing 6 peaks. So already it shows us that there is some degree of equivalence. There are some carbons that are sharing the what do you call it, the spectrum in terms of the peaks. So those carbons, equivalent carbons, they produce 1 peak. So we do have 3 pairs of carbons here, so we shall see which carbons are equivalent in our structure. So this is the information that we need to figure out. So given this information, what we need is to take note of the chemical shift values. Then we go to that chart that I'm going to show you now. So that chart, it will quickly help us to figure out what kind of carbons we are dealing with. So I want you to take note that this information about this chart, I think it varies with the textbooks. You see? So some textbooks, they can tell you different information, but basically it's not going to be that different. So this is something that you can use just to quickly figure out what's going on with your structure. So we have the chemical shift values between 0 to 70. They are for sp3 hybridized carbon, normally for primary carbons like this alkane CH3. Okay, so a primary carbon is the one that has got only 1 hydrogen substituted, and it is bonded to another 3 hydrogens. Okay. Then if you have carbons that are showing a chemical shift values between 70 to 100, then it's either an sp2 hybrid carbon or an sp hybrid carbon. So 100 to 120 is sp2, which can actually either an alkane, okay, or an aromatic carbon. Okay. Then for this one, it's either a CO or a CN. So in this case, we cannot talk of a CO because we don't have oxygen in our structure, but a CN is possible. Then the last one, between 120 to 210, is for sp2, which is also for aldehydes. So this one we cannot also consider it because we don't have oxygen in our structure. So let's go to what is happening in our structure. So this is the information that we are trying to interpret. Okay, just a moment. Okay, there we are. So these are the chemical shift values that I managed to deduce from the chart. So we have a chemical shift at 39, 98, 110, 160. Sorry, not 160, it's 120, sorry. It's 120, then 134 and 153. So this one at 39, it falls under these primary carbons, the alkanes, the CH3. So the chemical shift of this carbon is the one which is showing a quartet. So normally it's in a quartet, yeah. So normally the shielded carbons, they are, what do you call it, their spectrum, they appear at a low chemical shift value, okay, which is the upfield side. Then the value at 98, it's actually telling us that we have a CN, because we can rule out the possibility of a CO if you remember the chart that I showed you. Okay, let me just bring that chart close so that things make sense as we interpret this. So the 98 peak, if you check, it's falling here. So we cannot consider the CO because we don't have an oxygen. So CN is a possibility. Then we have a peak at 110. So 110, it falls here, where we say it's an sp2 hybrid carbon, which can be an aromatic carbon or a carbon on the double bond, the alkene. Then we also have the 120, 134, and 153. So still they are falling in the same region here. So basically, this is the information that we have as far as interpreting our structure is concerned. So now we now need to figure out, so we have this carbon, right, the CN bond, then we have these aromatic carbons, then we have these primary carbons like this. So this actually can give us an information of what is happening. So we have 1, 2, 3, 4 carbons, okay, on the benzene ring, right? Then we have this carbon, right? And we have these carbons. So now we just have to picture out now our structure, and also concerning, if you also check here, the hydrogen spectrum, I didn't talk about the integration. So the integration, it actually shows you the ratio of the hydrogens that you are dealing with. So if you check this integration, it's more or less like it's a 1:2 with this one. So yeah, it's a more or less 1:2 or 1:1.5, which means 2:3 sort of. So we'll see how this is gonna also come into play. So now this is my trick. Once you get this information, now you're now trying to put pieces together. If you remember from the mass spec, I said we have a benzene ring and a triple bond, if you remember. Then we also did that interpretation of the IR where is it? If you are following that interpretation, we had this double bonds, okay, and you also have this double bonds, then this one is a triple bond. So now we can actually try to visualize our structure here. So my trick, one that I have learned, I know sometimes it can be difficult to deduce the structure, but normally when you have interpreted your pieces like this, it's easier to get a clue because you can simply Google. So when you Google C9H10 N2 with an idea of what is the composition of your structure, like now you know there's a benzene ring, there's a triple bond, there's also a carbon bonded to a nitrogen, and you are also expecting to see the CH3 carbons, the primary carbons. So it can give you a clue of what kind of a structure it is. So when I Googled, okay, I found something like this. I'm just gonna quickly draw it, then I'll discuss with you. It was exactly the thing that you're looking for. So basically, to put all that information together, this is the structure that I came up with. Okay, when I just Googled, because in my mind, remember, I was expecting to see a carbon to nitrogen triple bond, right? I was expecting to see the CH3 carbons, okay? And I was expecting to see the CN carbon to nitrogen bond, if you remember, from the carbon NMR. I'm just gonna show you now carbon NMR, if you remember. So for the carbon to nitrogen triple bond from the IR, then so the carbon to nitrogen bond, this one, and the CH3, then the aromatic carbons. So basically, this structure, I found it more appealing. And why do I say so? Because if you check here, you're gonna have this carbon and this carbon. It's your first pair of equivalent carbons. And in terms of the splitting pattern of this is the carbon that are giving us a quartet, because they have 3 hydrogens attached to it. So because they are equivalent, they give us 1 peak. Then if you check this carbon and this carbon, right, they are equivalent, okay? Then this carbon and this carbon, they are also equivalent, so they give us 1 peak, which is a doublet. So if you check in our carbon NMR, we have 2 doublets in our carbon NMR. Okay, so we have 2 doublets. Then for a singlet, we have 3 singlets. So we have 2 doublets, 1 quartet, and 3 singlets. So for the singlets, we have this carbon, we have this carbon, and you have this carbon, you get those singlets, peaks. So in terms of the HNMR, so if you check on the HNMR, we have singlet. Like here, you don't have any neighboring hydrogens, you get a singlet. Then the hydrogens here on the benzene, they give you a, what do you call it, a doublet. Okay, they give you a doublet here. Then actually that's the information that we have, because if you remember that part when I said we have a small peak which I'm going to give a benefit of doubt, it's not really making sense if we should consider it. If you remember very well, where is my question here? Okay. Okay, I'm looking for this, sorry. So, if you remember on my hydrogen spectra, this one, there was a part that I was saying it's not really appearing very, but I'm just going to give it as a benefit of doubt. But I don't think it has a part to play, because as you can see, we have these doublets due to the two pairs of hydrogens on the benzene ring, those two pairs of equivalent carbons. Then we have a singlet due to those, what do you call it, the CH3 carbons attached to a nitrogen. Okay, so basically this is the interpretation of this spectra. So unfortunately I did this in parts so that you can be able to follow bit by bit. So this is the structure that I came up with, which is actually convincing. So normally the challenge is on putting things together. So this is why myself, I've adopted this simple technique of just, once you have your pieces of your interpreted data, you can simply Google. So when you Google your C9H10N2 based on the variable structures, you will actually be able to pick out the structure that is corresponding to the pieces that you have. But I'm gonna show you another approach on putting pieces together on the next coming videos. I would like to thank you for following up and also paying attention to my video. If you have any questions, please don't hesitate to ask. I'm always willing to assist. I'm someone who enjoys chemistry, and I've been assisting a lot of students. So especially for second year students doing chemistry, yeah, if you have any challenges, there is someone who is here for you, and which is myself, Simbarashe Karambwe. So guys, if you enjoyed this video, please show by liking my video, and I hope to interact with you guys in the next coming videos. I'm going to be posting a lot of videos based on tackling some of these chemistry challenges. So if you have any problems, you can also email me on my email, karambwe sim@gmail.com. So Karambwe is KARAMBWESIM@gmail.com. Then I'll quickly respond to your call. So thank you for watching this video. Please just like my videos, then we are good to go. Okay, This is pi for me.